Okay. Um, yeah, good afternoon, everybody. My name is Pablo, and I'm going to present my work on combining the density-based compressible solver or central foam with the reacting flow solver reacting foam. I start with a quick introduction. First, I want to define what is compressible flow. So it occurs when the fluid density changes significantly due to variation in pressure or temperature. This phenomenon is very important in high-speed aerodynamic, propulsion system, gas dynamics, and combustion in general. There is a key parameter that we use. It's called the Mach number. It's defined as the ratio of the flow velocity to the speed of sound. We say that when the Mach number is bigger than 0.3, the compressibility effect becomes significant, and we cannot neglect them anymore. So here I show two nice pictures. On the left, we can see it's an FA-18 breaking the sound barrier, which demonstrates the shock waves in high-speed aerodynamics. And on the right image, we show a NASA Mercury capsule in a wind tunnel test, which highlight also the shock structures caused by supersonic flow. So in those cases, compressible flows, they require solvers capable of accurately capturing the shocks and the discontinuities and the rapid variations. This brings us to the two main approaches for solving compressible flow problems, so density-based and pressure-based solver. Here I compare the pressure-based and density-based solvers on different aspects. For pressure-based solvers, the pressure is used as the main variable, and we solve a pressure velocity density coupling through a pressure correction equation that you derive from the continuity and the momentum equation, like it's done in the simple and piezo algorithm. We usually will use implicit time schemes, which allow larger time step, but also introduce more numerical diffusion and could smear the sharp gradients. They are commonly used for steady state problem or transient flow with large time steps, but can struggle with accuracy in convection dominated flows. In the other end, density-based solver, like those based on Godunov methods, use the density as main variable and usually explicit time schemes that would minimize numerical diffusion, making them better suited for the sharp gradients and to capture discontinuities. The pressure is usually calculated from an equation of state that links the density to the pressure and the temperature. They perform better in compressible flow with shock and discontinuities, but they also require smaller time step and can be less robust for a low speed flow. Now we'll quickly talk about reacting flow. So reacting flow refers to fluid movement with chemical reaction, such as the one that we find in combustion, where species transport and heat release significantly influence flow dynamic. So CFD is important in predicting and optimizing processes in industries like aerospace, automotive, and power generation. It's useful like for analyzing flame stability, pollutant formation, and combustion efficiency. In open foam, so the most widely used reacting flow solver is reacting foam, which employ a pressure-based pimple algorithm. However, there is no density-based reacting flow solver currently available in the official open foam release. And a density-based approach can be relevant for combustion because it handles high-speed flow and large density variations better. It also captures acoustic wave dynamics, which are crucial for understanding interaction between heat release and acoustic phenomena, which is especially relevant in systems with thermoacoustic instability. So this highlights the importance of developing a density-based solver for reacting flow. So after this quick introduction, I will present you the theory of reacting flow by showing you some governing equation, and then I will present the theory of the central scheme. So the governing equations solved in reacting flow are the following. So I guess we will see them a lot during this week, so I won't go into too much detail. But basically, we have the Navier-Stokes equation plus one transport equation for the species mass fraction YK. So for every species being considered, and an energy equation. So here I wrote two different forms of the energy equation, since in OpenFOAM you can choose which one you want to solve, either in terms of the sensible enthalpy HS or sensible internal energy ES. There is also an equation of state that links the density to the pressure and the temperature. So here I use the ideal gas law, with W being the molar mass of the mixture and R the ideal gas constant. So some precision on those equations. The sum of all species mass fraction should be equal to 1. In OpenFOAM, in the species transport equation, we see the diffusive flux, and it's expressed assuming Fick's law, and with the Lewis and Prandtl number equal to 1. So the diffusivity of each species is equal to the viscosity. This is wrong in most cases, and more precise diffusion models are required for better results. Finally, in the energy equation, we have the heat flux, which is expressed as follows, with lambda, the heat conductivity of the mixture. Now what I will show is how the convective fluxes can be discretized using the central scheme theory. So the convective terms are here highlighted in red in the equation. So these schemes were introduced by Kurganov et al., also known as Kurganov-Tadmor or KT, and Kurganov-Noel-Petrova KNP schemes. In compressible flow, so the information travels not only with the flow velocity, but also at the speed of sound. So this means that you have to account for waves that are propagating in all directions. And the central scheme, they handle this by discretizing the convective fluxes by considering these wave speeds to accurately capture shock waves and discontinuities. So here in the diagram, we have two control volumes separated by a phase F, which each state variable has its value stored at the cell center P and N, with U that represent the fluid velocity, and C is the speed of sound at which waves propagate in every direction. So here I show the integration of a convective term over a control volume using the divergent theorem. Usually in incompressible flow, you would interpolate the mass flux linearly and the variable psi using a scheme that includes some degree of upwinding. But in this case, for the central schemes, the flux term are integrated and linearized over the control volume, and the interpolation is performed in both directions using a weighing factor alpha and a diffusive flux omega. So before I show you the formula for alpha and omega, you can see that here the value of P and Psi are interpolated in two different ways. Here indicated as F plus and F minus in the subscript. So F plus means that the value is interpolated onto the face F from the P cells toward the F plus direction, while F minus you interpolate from the N cell in the F minus direction. The weighing factor alpha determine the contribution from positive and negative directions. So depending on whether you use the KT or KNP scheme, it's expressed in terms of volumetric fluxes, noted as AF plus and AF minus here, which accounts for the speed of wave propagation. So you can see in their expression, you have the speed of sound multiplied by the surface of the cell. And finally, we have the diffusive flux omega, which is included to stabilize the solution. So now I will describe how is the reacting foam solver implemented and go through the main point of the code. The thermophysical model thermo in reacting foam is the first thing that's constructed in the createfields.h header file, which is based on the thermophysical properties file located in the constant folder. This file defines the thermotype dictionary, which specify a combination of thermophysical parameters such as a transport model, energy variable, and equation of state. Then the mass fraction are set up using species information from the reaction and thermo.compressible gas files. And we also have in this create field refs.h the temperature and compressibility that are defined as references for a later use in the solver. So in this slide, I show an example of the reaction and thermo.compressible gas file used in a reacting foam. The reaction file defines the chemical reaction involved in the mechanism as well as the species. It also specifies the reaction types, such as here, reversible Arrhenius reaction, along with key parameters like the pre-exponential factor A, activation energy TA, and temperature exponent beta. The thermo.compressible gas file provides a thermophysical property for each species, such as molecular weight, specific heat coefficient, and transport properties. So in this example, it's for the O2 species. We specify the molecular weight and the thermodynamic coefficient over a defined temperature range. So following, fields such as density, velocity, pressure, and compressible mass flux are created. Additionally, the pointer reaction is initialized, which provide access to the chemical source terms. The species mass fraction yi and the energy variable are added to the fields table for interpolation during the simulation. And finally, we have the Q dot field, which is the heat release rate, which is created to calculate the energy release by the chemical reaction of combustion. So what you see here are the main line of the reacting foam solvers. The density field is first calculated by solving the continuity equation. Then the momentum equation is solved, which compute the velocity field. And the reacting species transport equation are solved, followed by the energy equation. At this point, the solver enters the while pimple correct loop, which is the inner corrector loop where the piezo algorithm is executed. So that's a key feature of pressure-based solvers. The pressure velocity density coupling is resolved using a simple and piezo algorithm instead of calculating the pressure directly from an equation of state, which is one of the main difference density-based solvers. Here are described in more detail the y, e, q, n dot h header file. The line, the reaction correct line computes all species reaction rates, while the q dot equal reaction arrow q dot retrieve like the updated heat release rate per unit volume from the turbulence chemistry interaction model that you've chosen. So for each reacting species, a transport equation is solved, including term for the temporal derivative, the advection terms, the diffusion terms, and we also include the chemical reactions. We see here that the diffusion terms also include the effective kinematic viscosity, which accounts for contribution from turbulence and laminar flow based on the selected models. The negative fraction are avoided by clamping the value to 0, and their sum is updated. Then the mass fraction of the inert species is computed from it's the remainder of the total of the sum, which allow you to solve one less equation for the species and consume less computation. So same as for reacting foam, now I will describe how raw central foam is implemented. The create field refs.h and create field.h files used in raw central foam are shown here. So first, the Boolean variable inviscid is initialized as true and later updated based on the viscosity mu. If the viscosity is non-zero, the flow is considered viscous and the variable is set to false. Similar to reacting foam, the thermophysical model thermo is created using the thermophysical properties file in constant. So additionally, the thermodynamic class used in psi-thermo is not psi-reaction thermo anymore, since raw central foam focuses on compressible flow without chemical reactions. However, in raw central foam, so the energy variable is referred to as E, the sensible internal energy, instead of HE, the sensible enthalpy. Sorry. So in raw central foam, there is only one way of solving the energy equation, and it's in terms of sensible internal energy. Then the solvers solve the governing equation, but for the conservative or density weighted field. So we declare those variable by multiplying the fields with the density, and the total energy is also declared using this formula here. So in order to interpolate in both directions, as I mentioned sooner, we create two surface scalar field variables, pose and neg, and we declare them simply as uniform 1 and -1 dimensionless scalar. They will be useful for the interpolation in both directions. So the first step at the beginning of the time loop is to compute the interpolated field in both directions. So that's what is done here for every useful variable. This is done using the interpolate function, which is declared in the direction interpolate.h file. And the interpolation is done by using the scheme that you specify in the interpolation scheme dictionary of the FV scheme file. So the syntax is a bit different. Basically, in this interpolate function, they will read the scheme that you are using, but you have to write reconstruct, parentheses, and the name of your field. Otherwise, you won't find it. Following, so we compute the local speed of sound, which is calculating using this formula, with gamma being the ratio of feed capacity at constant pressure and volume. It is also then interpolated in both directions and multiplied by the surface area of the cell faces to obtain the associated volumetric fluxes. Then we have AP and AM, which correspond to IF plus and IF minus that I defined previously as those two values. So that's what is basically done in the script on the left. Once we've done that, we have all the necessary value to compute the weighing factor alpha and the diffusive flux omega. They will have different value depending on the chosen scheme, KNP or KT. So that's what it's done in the code on the left. I rewrote the formulation of alpha to help. And finally, we compute two terms for AFV pose and AFV neg that I highlighted in red in the equation here. So you kind of rearrange the equation to have like those two terms that are factor of the different conserved variables. So we can now compute the linearized convective terms of the governing equation simply by multiplying by the density weighted field as it's done for rho u here, for example. So you see the AFV pose and AFV neg here, just multiply by the interpolate rho u in the positive direction and interpolate rho u in the negative direction. And finally, so we can solve the governing equations. First, the continuity is solved explicitly. Then the momentum equation is solved, but in two steps. So we first solve the inviscid equation, so without the viscous term. So that's the first line here. You can see that we only have the time derivative and the convective term. Then after updating the velocity field u, the diffusive term are added implicitly to the equation if the viscosity is non-zero. So you see this this if statement here, and if the viscosity is different to 0, then you add the diffusive term, as you can see here. And this one is added implicitly, and this one explicitly. A similar procedure is done for the energy equation. And finally, the pressure is computed from the ideal gas law that you see here, and I show you at the beginning as well. So now that you understand, I hope, a bit better how both solvers are working, I'll describe the implementation of reacting rho central form, which is the addition of reacting species transport equation within the rho central form solver. So the first thing is to modify the thermo object and to declare the species mass fraction. In this case, we will use a C reaction thermo instead of psi thermo, since we want to take chemical reaction into account. So it's the same as in reacting form, but additionally, we declare a list of pointers to store the density weighted field needed for the implementation of the central convective fluxes in the mass fraction equation. So that's what is done here, basically. PTR list, you can see this new one. Yeah, that's a new line. Here, what we do, we set the density weighted mass fraction in the Poitron list rho y. Each variable will be called rho followed by the name of the species. So that's what we write here, rho plus y name. And the variable yi and the energy he are added to the fields table, so here and here, for interpolation. And we make sure that the density weighted field are not read or written to disk automatically with the IO object flag, because we don't want to save those fields basically to the memory. That's what's done here. So to solve the reacting species transport equation, I created a new header file, oyeqn.h, include after solving the momentum equation. So that's a modified version of the yeqn.h from reacting foam with the convective flux that are adapted using the same procedure as in raw central foam for the other fields. What we do first, so we solve the inviscid transport equation. We do without diffusive term and chemical source term. That's what's done here in this line. Then the mass fraction is updated and its boundary are corrected. After what, we solve the equation with the viscous term if the fluid is non-inviscid, and we add the chemical source term as well. You can see here the full equation, so the time derivative, the implicit, the diffusive term that are implicitly, and the chemical source term. So that's if the fluid is inviscid. No, that's if the fluid is not inviscid, and if the fluid is inviscid, then it's the same basically, but you don't add the diffusive term. And finally, the rest of the end of the code is similar to reacting foam with the computation of the inner species mass fraction. So we now present two test cases that I ran to validate the new solver. The first one is the 4-step case tutorial, which is used as the first validation in order to see if the solver is able to reproduce the results of raw central foam on a non-reacting configuration. So this is a Mach 3 flow in a wind tunnel facing a step. It was introduced as a test, like for the accuracy of numerical schemes, and the properties are set such that the speed of sound is equal to 1 meter per second in the medium. We use a structure uniform mesh with a length cell of 1.25 centimeter and a CFL number of 0.2, and we ran this case for 4 seconds. So yeah, that's kind of a sanity check to see if our implementation doesn't crash for this case, which is a bit more basic. So here I just present how you can set your medium such that the speed of sound is 1 meter per second. Basically, the speed of sound can be computed this way, and by setting the right value in uthermo.compressible gas, you can retrieve that the speed of sound is equal to 1 meter per second when the temperature is 1 Kelvin. Here are the results after 4 seconds for both raw central foam and reacting raw central foam. So the result of reacting raw central foam are mirrored to the x-axis, so we can really compare well both results. They are qualitatively identical, which is a first good validation of the new solver. But I would also like to show you a video. Let me know if anybody can tell me if you see the video on the screen.
Yes, it worked.
Okay. So what I did basically on the top is raw central foam, and on the bottom is sonic foam. Sonic foam is a version of raw pimple foam, but more adapted for trans and supersonic flow. So I ran both cases for 4 seconds. And you can already see the difference between both cases. On the bottom, the discontinuities, they're a bit less, not as good defined as on the top. The gradient are smeared and they're not as sharp. I can run until the end. Also, the location is a bit different. For this test, they say that at 4 seconds, like the leg of this shock should be aligned with the step. And we see here that the location is also different. So you can see that in this case, even if the sonic foam should be more adapted for transonic cases, it doesn't perform as well as a density-based solver, which is already a good sign of an improvement for this kind of configuration. The second test case that I did is the 1D reacting shock tube. It's an inviscid mixture of H2O2 and argon with a pressure discontinuity in the middle. So basically you start the simulation and a shock is created because of this high pressure difference. The shock will be reflected on the left, on the wall, and the temperature will increase, and that will create a reaction wave. The domain is discretized with 2,400 uniform wind points, and the CFL number is set to 0.1. So that means that the one cell is 50 micrometer long. So something that's worth mentioning. So for reactive case, you need a chemistry mechanism that include all the necessary species and reaction that you want to consider. In this case, I obtained the ChemKin files from Lee et al. Of a chemistry mechanism for H2 combustion, which I converted to foam format using the ChemKin to foam utility. The file, they are then created and stored as reactions and thermo file in the constant folder. And so here you can see the line plot along the 1D domain for the temperature, velocity, and the hydrogen mass fraction at 3 different times using reacting row central foam and reacting foam, and compare with the reference solution of the literature. We see that reacting row central foam works better in this case. The discontinuities are well predicted and well located compared to the reference case. In the other end, reacting foam schemes introduce more numerical diffusion. I think in this case, I use second order linear schemes for the advection terms. And yeah, we see that basically the discontinuity are not perfectly located compared to the reference case. Something that's interesting or worth mentioning as well, I was able to get better result with reacting foam, but I had to increase the number of inner and outer loop, and my simulation time increased by a factor of 4 and 5, which you see that in those cases, you kind of lose the advantage of pressure-based and algorithm and implicit method, because so you want anyway, you want a small time step to reduce numerical diffusion. And if you have to increase the number of inner and outer loop, then your calculation is even slower. And that's one of the point of using pressure-based algorithms to use bigger time step and to have a quicker simulation. Okay, so that's what I was just talking about. So we'll now finish with the conclusion and the future work that can be done. As you see, I developed successfully reacting row central foam, which can be seen as an extension or combination of row central foam with reacting foam. The solver, so I validated it against well-established test case in non-reacting and reacting configuration, showing good agreement with the literature. It outperformed reacting foam in the supersonic case, showcasing like the superiority of the central scheme in such scenario. So in the future, I would like to think, so maybe extend the solver for low speed flow by introducing more robust schemes that could work in a wide range of Mach number. And also the fact that the solver is explicit in time may be easier to implement higher order schemes. And finally, could integrate more advanced transport and turbulence chemistry interaction model for a more precise combustion simulation. So yeah, my presentation is now finished. So I hope you enjoy it and you learned something. And if you have any question, I will be happy to answer it. Thank you.